Hi, and welcome back to this series of videos that I'm pretend to release. Um, my goal is to cover this book, Introduction to Robotics, which is from this author, SAEED NIKU. And on the first video, we start covering the chapter 2, and we stop on the topic 2.4.3, which is the representation of a referential on the region of a fixed reference system. Let me write this, the representation of a referential on the region of a fixed reference system. And do some note of this point, which is really important, referential and fixed reference system. And the book says, as we a referential is generally represented by three axes mutually orthogonal. And what this is mean is very simple. On the zxy plane, on this 3D plane, xy, uh, orthogonal means do a 90-degree angle related from the other axis. So right here, x is doing a 90-degree with the axis y, and the axis y do also 90-degree with the z-axis, and that is the same for the x-axis is doing a 90-degree angle with the z-axis. Okay, and as we can have more than the one reference at the same time, we use we will be using x, y, and z for representate a fixed reference system from a universe, like let's say f of x, y, and z, and this is a fixed reference system. And also we need to use a set of axes n, o, and a to represent other referential, but now this is a movable referential. This is will form this movable reference system, and n means normal, o orientation, and A is for approach. So let me draw a, a robot arm so you can understand better what I'm trying to illustrate with what I'm trying to explain with this reference, this fixed reference system, and this one, but this is movable. So let's say we have this robot arm, and now we can represent the axis for the fixed reference system. So I forgot to draw the base. Right here we have a base, and this robot arm is fixed on this base. So we have this reference system in this fixed point. So right here is this reference fixed reference system, and right here we have this other reference system, but this is not fixed, is moving. O, N, and E. Okay. So each direction of each referential N, F of N, O, and A localized on the region of a reference system. This one is represented by his three cosines. Director cosine related to a reference system, like you're seeing on this figure, and consequently the three axes of the referential can be represented by three vectors on the matricial form this way. Nx, Ny, Nz, Ox, Oy, Oz, N, Ax, Ny, N, Az. Now let me illustrate the representation of a referential on the region of a reference system. This is the reference system. And now let's represent the referential. this way. And let me change the color to do the decomposition of the components. I forgot to draw right here this component, this vector. Sorry, this axis. Oh, that is an axis. This is two, and this two. And now we will do the decomposition. OZ, OY, and OX. And this topic is very short, and we already are on the topic 2.4.4, and let me be quickly on this. We wanted to describe a completely a referential related to other referential. So let's write this matrix OY, OZ, and 0, and you will see why we are completing this matrix with this line. Which means this vector, the vector P, it has a direction different of, is not on any of these axes actually. Okay, and we can now illustrate this matrix, represent this matrix with the with this plane, this reference, and the vector P itself. And the mobile referential. And I already mentioned on the first video that is W, the factor of scale, and I said P is positive and is on a direction which is not we cannot we can decompose on these other reference components of these reference systems, but for the vector p actually are not uh, perpendicular at any of these axes of this reference system. And we can jump in on this example 2.3, which says that a referential f which has this matrix form and or localize it 3, 5, and 7 units with the axis n parallel to the axis x, 90 degrees. Okay, and also it has your axis 45 degrees. Um, the axis O is 40 degrees related to the axis Y, and the axis E also 40 degrees with the axis Z. And if you remember, let's do this quickly. Cosine of 45 degree is equal to the square root of 2 over 2, which is equal 0.707. And of course, for sine, we have minus 0.707. And drawing the representation of this vector on the reference, the vector P. This reference, which is the movable reference, and right here, and 90 degrees with the axis X. So is on the same direction. Same direction is on the same direction. That is Z, that is X, and that is Y. And as you can see, 90 degrees, which is the same as perpendicular or orthogonal, and is on the same, is perpendicular to the x-axis. And let's see, right here, O is 45 degrees. It's forming 45 degrees related to the axis Y. So the axis Y forming is just to do the decomposition. If we do the translation of this axis Y right here, let me see. If we put right here, it's forming 95 degrees. See? And let me draw this. The vector A is forming 45 degrees related to the axis Z. A 45 degrees related with Z. Related to Z. And that is how we obtain these values. Okay, so we're still on the chapter 2, and that was the topic 2.4.4, the topic that we just covered. And we also cover on the start of the video this topic. So on the next video we will start covering the topic 2.4.5. That's it. Thank you.